Okay, geometric sequences. We've talked about arithmetic sequences before. Arithmetic sequences involve the first term of the sequence and the common difference between the terms. We did that a long time ago in this class. It's like chapter 3 or chapter 2 or something. So it probably seems like forever ago. So long ago that you probably forgot. Well, in this section we're dealing with geometric sequences, and really we haven't said it, but you've been working with geometric sequences in the last two sections. The last two sections dealt with exponential functions, and that's really all geometric sequences are, is an exponential function. Geometric sequences involve the first term of the sequence and a common ratio, not a common difference like arithmetic sequences had. So I'll talk about that common ratio in a little bit. This is a lot like the common ratio that we were doing in section 6. The base of the exponent is the common ratio. So to solve these problems, first find the first term, a sub 1, then also find the common ratio r, and then plug them into this formula sitting right here. A sub n equals a sub 1 times r to the n minus 1 power. And that is n minus 1 power in the exponent. It will always be there. A sub 1 is the first term of the sequence. R is the common ratio of the sequence, and then you're raising that to the n minus 1 power. This formula will give you all the terms of the geometric sequence. Okay, so the question is, which of the following are geometric sequences? First of all, in order for something to be a geometric sequence, it has to have a common ratio. Kind of like when we had arithmetic sequences, you had to have a common difference. So let me step to the side for a second here and come up with a different sequence. 1, 3, 5, 7, and so on. Is not prime numbers, odd numbers. Okay, so that's the pattern. These are all the odd numbers that are positive. This is an arithmetic sequence though, because, and hopefully this will jog your memory, what are we doing to go from 1 to 3? We're adding 2. What are we doing when we go from 3 to 5? We're adding 2. What are we doing when we go from 5 to 7? Adding 2. And that was an arithmetic sequence. From that, we could generate a formula, which was a sub n equals a sub 1 plus d times n minus 1. We just stick in the things that we know and then simplify it down. A sub n equals the first term, which was 1 in this example, plus d, which was the common difference, and the common difference here is 2, so times, or plus 2 times n minus 1. And then we would simplify that down, distribute the 2, and then combine like terms. So a sub n equals 1 plus 2n minus 2, so a sub n equals 2n minus 1. And then this equation allows you to calculate any term. Like if you wanted the 100th term, you'd say a sub 100 equals 2 times 100 minus 1, which would be 199. That's an arithmetic sequence. We're doing geometric sequences. We don't have a common difference here. We have a common ratio. So what we want to do is say 20 times what gives me 200? 10. Times 10. What about 200 going to 2,000? What did we do there? Times 10. And from 2,000 to 20,000? Times 10. And from 20,000 to 200,000? Times 10. So each time we have a common ratio. We're multiplying by 10 to get the next term. That's R. So is this a geometric sequence? The answer is yes, because we have a common ratio. We're multiplying by the same number each time. So to answer this question, it's yes. And we don't have to do this on this problem, but we might as well do it because it's good practice. We can now write the equation for this geometric sequence. It's very easy to do as long as you remember the formula for it. It's a sub n equals a sub 1, which is the first term, which is 20, then times, I use parentheses, not a dot, the common ratio, which is r, so that's 10, and then the exponent is always n minus 1. And that's the equation for that geometric sequence. They're very easy to come up with. Even easier, really, than the arithmetic sequence, I think. All right, let's take a look at the second one. Is that a geometric sequence? Good, it's not a geometric sequence. Why not? Yeah, it actually is adding by 1 each time, by 2 each time. From here to here is plus 2, from here to here is plus 2, and so on. So this one is no, it's not a geometric sequence. What is it though? Yeah, this one's actually an arithmetic sequence. And we could write the equation for that one just like we did over here using this formula right here. We're not going to. This one is arithmetic. This one's kind of a tricky one, this last one. What do you think? Is this geometric? Yeah, it is actually. Because why? Right, we're multiplying by -1 each time. 5 times -1. -5 times -1. 5 times -1. Each time we're multiplying by -1. So this one is yes. Geometric sequences can even have the same number every single time. And it's still a geometric sequence because in that case you're multiplying by 1 each time. And let's write the equation for this one too. We don't have to, but we might as well. A sub n equals what? 5, the first term, which was 5, times -1 to the n minus 1 power. That's right. And that's your answer. The directions on this one say write the formula for the sequence. So we've already done that a couple times. All you got to do is remember the formula. A sub n equals a sub 1 times r to the n minus 1 power. It's that easy. Now they're giving you pretty much everything you need to know here. Only thing you got to figure out is what? Well, that's given to us. You can see it. Just, yeah, the common ratio, r. Okay, that's all you got to figure out. So just ask yourself what's happening each time here. What are we doing to go from here to here? Multiplying by 3. And is that true here? Are we also multiplying by 3 here? And are we also multiplying by 3 here? Yeah, we do have to multiply by the same number all the way through, otherwise it's not a geometric sequence. So always watch out for that. But now that we know that, we can write the equation. A sub n equals what? The first term, 7, times 3 to the n minus 1 power. And that's the answer. So take a look at the second one. Is that a geometric sequence? Yes, because we are multiplying by 2 each time. So I'm going to write r equals 2 here, just so I remember, just in case I forget. As I'm writing out my equation, which will take me about 4 seconds, a sub n equals what? 2 times 2 to the n minus 1. Now here's a question for you. Could I take this 2 times 2 right here and just say 4 to the n minus 1? Wouldn't that be easier? Can I do that? Why not? The thing. With the thing? Order of operations. Order of operations says you have to take care of the exponent before you can multiply. So we can't do this right now because we don't know what n is, which means we can't multiply for sure. So this is the answer right here. You're just going to leave it like that. Even though maybe it looks weird to you, that's how you have to write the answer. How about this last one? What are we doing? Yeah, it's by 1/2 each time. It is multiplying. It's tempting to say divide by 2, but you want to think multiply. This is being multiplied by 1/2 each time. So that makes r equal 1/2. And then my equation is going to be what? Yep, times 1/2 to the n minus 1 power. And that's your answer. Now in the last couple of sections we've been working with equations that look very similar to this. They have the variable in the exponent, and that's exactly what's happening here. The variable is in the exponent. This is also an exponential looking equation. If you were to graph it, you would see a graph that looks like this. Or you could see a graph that looks like this. Or a graph that looks like that. Or a graph that looks like that. Okay? Same stuff, just different looking is all. All right, we got a couple more things we got to do here, and then we're done with the section, which means we're almost done with the chapter, which is nice. A geometric sequence has an initial value of 6 and a common ratio of 2. All you got to do is read this problem, and they've told you everything you need to know. Write a function to represent the sequence, but now they want to know what the 8th term of the sequence is. So, we have an initial value of 6. What does initial value mean? Yeah, that's what you started with, which is, which term? What do we call that? Yeah, that's a sub 1. And then it says a common ratio of 2. What's that? That's your r. So they've actually given you everything you need to write the equation right away. Just because there's words there doesn't mean it's impossible. What do I write? A sub n equals, yep, a sub 1, which is 6, parentheses, r, which is 2, time to the n minus 1. Okay, now they want the 8th term of the sequence. So a sub 8 equals 6 times 2 to the 8 minus 1. We just substitute in 8 for n. What do I do first? Yep, exponents first. Now actually that says 8 minus 1, but we know that that's what? Yeah, that's 7. So what I actually have here is a sub 8 equals 6 times 2 to the 7th power. You can type that straight into your calculator to get your answer. 2 to the 7th power is 2, 4, 8, 16, 32, 64, 128. 128 times 6. 256 times 3. What's that? 768. So there's your 8th term in the sequence, 768. All right, the second problem sitting there is very similar to the first one. Go ahead and give that one a shot. So it says the geometric sequence has the initial value of 64, common ratio of 1/2. Write the function in it to represent the sequence, and then find the 5th term. What do I need to do? What? A sub n equals 64 times, good, to the n minus 1. That's the equation. Now what? Okay. To the 5 minus 1, which is 4. So now you can type that in your calculator, or try to do it in your head. A sub 5 equals, that'd be 64 to the 1/2, or times 1/2 to the 4th. Well, 1/2 to the 4th is 1/2, 1/4, 1/8, 1/16. 1/16 times 64 is 64 over 16, which is probably 4. There's your answer. That's it. Section's over. Chapter's done.